Okay, so this is lecture 4. So today we will end our chapter 1 introduction and move to MOS transistor theory. So although this course is not for device physics itself, but it is important to understand the basic operation principle of our MOSFETs. So yes, first of all, let's review our previous lecture, lecture 3. So in our previous lecture 3, we have introduced multiplexer. So multiplexer simply select one of them, one of the input signal. Let's say D0 and D1 is provided, and there is a select signal, and depending on its value. If the select value is 0 and this D0 is selected and D1 is selected when S select is equal to 1. So this is a multiplexer, and in order to implement the multiplexer, we need tri-state gate. So we can implement the multiplexers using the tri-state. So how can we implement this tri-state? We have studied two different ways. One was using transmission gate, and another one is use tri-state inverter. So tri-state inverter simply has a form like this. So usual inverter driven by our input A. However, that is so if we have this kind of thing, then that will be just a normal inverter. However, here we introduce the select signal or enable signal here. So only when enable signal equal to 1 and enable bar equal to 0, then this inverter is turned on. So this can be simply done by introducing serially connected also NMOS and PMOS driven by enable signal and enable bar signal respectively. So that was the first one. After that, the second half of our lecture was devoted to the CMOS fabrication. So we started from the cross-sectional view of our simplest circuit inverter, and the lecture progress up to N-well formation was shown. So even this N-well formation, what was the N-well formation? Starting from our blank bare silicon wafer, so which is sometimes p-type. Our N-well formation just says that we wanted to introduce a small area, given area where its polarity is no longer p-type but n-type. So this part is called as n-well. So it is quite easy to understand from our viewpoint. So first, 누구시죠?
애들
이번에 처음
이번 새벽에
새벽이요? 네. 어쨌든 빈자리에 앉으시죠. 수업이 끝나고 좀 얘기를 하도록 하죠. Okay, so although it is easy to introduce such kind of thing, so if we just draw this one, okay, starting from our blank wafer, make a well and well. So that was done in our previous lecture. But please remember that in order to make this kind of fabrication, what we need were lithography and ion implantation and thermal diffusion. Of course, in between we have many intermediate steps like etching or something like that. So therefore, although we say we do certain patterning or we do certain kind of a deposition, so it is actually related with several sub-steps in it. So please note that it is not that easy. However, anyway, we have arrived at this annual formation. Now let's assume that we now have an annual. After that, we will make many different patterns on it. But please note that always when you say that we pattern this, we pattern that, then it is related with use of lithography and related photoregister stripping and some cleaning procedure. So we are just showing the most important ones, and let's continue our CMOS fabrication part. Okay. So now our previous status was just N-well formulated in the P-type substrate. Now we will make our P-MOSFET on this N-well, and here we will make N-MOSFET. Then how can we make it? So let's just follow our textbook example. And you know, this is really crystalline silicon. However, MOS system always need very good quality of gate oxides. So now we introduce thin oxide, and its thickness is around just a few 10 angstrom, so like orders of nanometer scale. However, I have to emphasize that this pure silicon gate oxide is applying for somewhat old technologies, and nowadays in reality thin oxide is no longer thin oxide. So yes, that was a previous one, and nowadays what we do is like this. So here we have a steel insulating layer, and this is called as steel gate oxide layer. However, it is actually done by two intermediate steps. Here one extremely thin layer. How thin is it? It is just one monolayer of silicon dioxide. Who made it? So we have not intentionally made it. So this is automatically, naturally grown by just the oxidation of our silicon substrate. There is one atom layer here. After that, here we introduce hafnium oxide. Hafnium oxide is introduced here, and that has higher permittivity. So I'm not quite sure whether you have learned about permittivity, but this is related with the strength of your insulating layer as a capacitor. If this permittivity is high, then even though you have a very thick layer, but it has strong capacitance. So if you have very thin layer, however your permittivity is quite low, then it is corresponding to a small capacitance. So are you with me? So depending on the material composition, you have different permittivity values. For example, what is the permittivity of our relative permittivity with respect to the vacuum? So in the case of air, this is quite close to 1. And how about our silicon dioxide? Then it is known that it is about 3.9 times higher than silicon dioxide. So simply speaking, when you have, let's say that, when you have 3.9 nanometer thick silicon dioxide layer, and let's compare just air gap, and its thickness is just 1 nanometer thick, then effectively these two layers have the same capacitance, because it has, although this is thicker, so seemingly having lower capacitance. However, the material filling the gap is having more higher permittivity, so that's the reason why they have effectively the same capacitance. And in the case of a hafnium oxide, so the value is about 20 something, 24, 25 or something like that. It means that even when we have 25 nanometer thick hafnium oxide layer, but its capacitance is actually equal to that of 1 nanometer thin air gap or 3.9 nanometer silicon dioxide. So are you all with me? So that's the reason why nowadays, instead of extremely thin silicon dioxide, we introduce relatively thick hafnium oxide layer. So this is usually high K materials. Why that is high K? K is used, sometimes used to represent the relative permittivity. So simply speaking, nowadays we introduce relatively thick layer of high K material to make this uh, insulating layer. So the quality of this gate oxide layer is quite important, and as we will see in this lecture today, so it really determines the capability to collect electrons and holes in the case of MOSFET and PMOSFET. So that is quite important. And let's come back to sometimes my pencil doesn't work. I have to wait for a while. Okay, now it works. And also we have another one. On top of this gate oxide, we grow the polysilicon, and this polysilicon was used as material for metal. So this polysilicon layer is used for our gate material. So simply speaking, usually when we consider the shape of our cross-section of our MOS transistor, what we draw is like this. Yes, we have substrate and n-type source and n-type drain, and here we have a gate oxide extremely thin. After that, we say that this is gate. That's the reason why our MOS symbol just looks like this. Maybe you remember this one. Here we have certain symbols like this. However, think about this gate. How can you attach our gate? Actually, gate is a metal, very relatively large structures. And how can we connect this metal to this point where the oxide, our thin gate oxide, and our material something? We need some glue between this interface and our large metal line. So what is it? So previously we introduced polycrystalline silicon, sometimes called as polysilicon, to attach our metal and this gate oxide. But nowadays, instead of polysilicon, now we use metal as a gate material. So this is this is a somewhat old technology, and sorry about that, but this is the textbook material. So please keep in mind that although we have two important components of our transistor, one is gate oxide and one is gate material, but nowadays gate oxide is actually hafnium oxide and gate material is not polysilicon but metal. So anyway, now we have to make a patterning. So now After this procedure, you will say that here we have patterned oxide and polysilicon and patterned oxide and polysilicon. Although we draw in this way, what we have to do is actually, first of all, so everybody now understand, in order to achieve this kind of goal, first of all, we have to introduce a layer of a photoresistor. So here we have first photoresistor, and some part is exposed. Yes, this part and this part is exposed by our light here selectively. Which one can make this selective exposure? So that is done by our mask, photomask, and the photomask looks like this. This is top view and this is a horizontal view, so only this part and this part is exposed. Then what will happen? After that, here we have two types of photoresist. This one is unexposed and this is exposed, and they have different properties. So this exposed one can be easily stripped. So now we have remaining photoresist here and there. After that, we introduce another etchant to etch this polysilicon. Then what will happen? This polysilicon is now gone, and also this guy gone, also this guy gone. Yes, then we will have pattern. However, here we have a very thin layer remaining in this part, so we have to change a different material to completely remove this remaining oxide layer. After that, of course, we have still here photoresist, and this one is also eliminated. Then remaining part can be written as just as clean as the next slide figure. Okay, so although I write down patterning, but patterning is all related with these intermediate steps, so please understand this kind of thing. Anyway, now we have defined our NMOS gate region and PMOS gate region quite clearly, and the next step should be the formation of our source, drain, and source and drain. How can we do that? So if we have a certain error in our photolithograph, the worst way we can expect is like this. For example, let's say that if we make this kind of thing, then what will happen? Unfortunately, our N-type and P-type are quite far away from this gate region. Then what will happen? This one doesn't work as a transistor, because when you apply high gate bias, then you will collect electrons. Wow, good, but that electrons cannot flow because here in between and within we have a non-channeled region, so non-gated region, so that doesn't work as transistor. Electrons cannot flow. Another worst way is like this. Wow. If we have such kind of thing, then our transistors has too short distance between our source and drain. Then what will happen? Then this transistor is working as just connected line and no longer working as a good switch. So please note that in digital application, when we apply 0 volt, then we should have complete isolation between this source and this drain. But if their distance is too short, then although we apply 0 volt, but direct punches through between source and drain is happening. So the best way we can imagine is just to make our N MOSFET, just to make our N plus region, source region, and drain region just aligned to the edge of our gate pattern. So how can we achieve this goal? Of course, this can be done by applying good lithography step, but please note that usually this distance here, how short is it? This distance, the distance of or length of our patterned gate is usually in every technology the minimum size we can achieve. So in this sense, we are doing our best to pattern this really short gate. So this is quite short, therefore controlling exactly the place or position of a source and drain was not that easy. However, fortunately with self-aligned procedure, so I will skip the intermediate step, and now we introduce this point and that point. Here, we will do certain type of N-type dopant implantation. For that purpose, we intentionally open only this part and that part. So, you understand the role of this part. Role of this part is to introduce our N plus region to have source and drain. Then what is the role of this opening even in N-well? In the case of P MOSFET, what we need is actually P plus region just around our P-type gate. However, now we are opening also certain region for our N-type implementation. So if you implant here, then you will have something like this. Now, if this is open, then you will have N plus region, and this N plus region gives you good electrical conductivity between this implanted region and here later metal for your connection. So here that part will be eventually connected to the power rail VDD, and this VDD is connected and N plus region, and eventually we will arrive at N well. So this part, this highly doped region is typically called as well tap, and this well tap is used to just to set the bias for our N-type well. Okay, so now this is understood, and now let's come back to our main purpose, source and drain. In this case, actually this is not that critical in case of photolithography. However, here this is really important because if we have made certain mistakes in this source and drain formulation, then as I told you before, we have unwanted shape of source and drain. That is quite critical, and what we have is self-aligned process. So self-aligned means that now previously it was open, then for this open range now we implant. Actually what we can say is implantation, ion implantation is not done only for this part. Even for this part, ions are coming. But what happens? Only for this open window and this open window, the silicon is exposed. And for other parts like this is protected. So if you have certain n-type implant, then N plus ions are located here, and also N plus ions are located here. But eventually that will be moved away. So that's the reason why our silicon substrate itself is safe from our implanted n-type dopant. So are you with me? So we actually have no idea, no way to selectively implant something into our wafer. Our wafer is entirely exposed to the ion beams. However, since we introduce a certain protective layer, then only for selected regions we can have ions inside it. Then now let's come back to our gate. Then what will happen? Wow. Even in this polysilicon will be exposed to our ion beams. So actually we will have N plus region and N plus region, and also we have N plus region for this gate material. So polysilicon in this case. However, point is, although we have this kind of thing, but this part, do you have N plus dopants or not? This gate material already patterned previously was used as also a protective layer. That's the reason why your gate region is quite much safe from this source and drain implantation. So simply speaking, this self-aligned process is the process where source and drains are self-aligned by predefined gate. So if you have a longer gate, then what will happen? Let's say that you have introduced a longer gate length, then still you will have source and drain just close to your gate end, because this one and that one be the reference points for your implantation. So if you have a shorter gate length, even in this case you will have well aligned source and drain shape. So that makes quite easy to fabricate our source and drain completely well aligned to our gate pattern. Please note that this kind of difficulty was aroused because this length is the minimum length we can imagine in our world. In this technology. This length is the shortest length we can pattern. So that's the reason why this self-aligned process is quite important. So now you understand, wow, when you do it, then now we have a well-made MOS transistor. Now we have a gate material and good quality thin oxide and P-type substrate and N-type source and drain region. The remaining thing is P-type substrate is not biased. P-type substrate should be biased to the ground. Then we need something, and also the remaining task is still we don't have a PMOSFET. In order to PMOSFET, we do the similar thing once again. So we can do it once again. Previously we had these ones, and now stripping all of them and do the same thing. In this case, now this already made n-type region is protected, and now the opening was done only for this one and this one, and we do the implantation. Of course, I wanted to say this one. When you just make an ion implantation, that is not the end of the story. So when you have the implantation, you will have ions, typically arsenic, and there will be so many arsenic atoms inside it. However, just after ion implantation, these arsenic atoms inside the silicon are not working as impurity because they are taking the position which is not effective working as impurity. So you have to introduce certain summer annealing, and that is done by applying certain heat in a short time. Then after this short time of summer annealing, then now your arsenic atoms are taking the place for perfectly fitted for the law of impurities. Then now you have activated impurities here. So please note that just after ion implantation, we have to do some heat treatments, and we do the same thing for P MOSFET. So now we have a P-type tab. So this is a substrate tab, and later we will introduce the metal connected to the ground, and now this ground voltage is propagate through this good perfect metal and good P plus region. So our interface between metal and P-type region is quite good, and also we have a homojunction, so same type P plus and P substrate, and eventually all of these P-type substrate are biased with ground. So that's the reason why we can say that so substrate of our N MOSFET is grounded, and at the same time our source or substrate of our transistor, P-type transistor, is biased to the VDD. So now let's go. Although we have now more or less the N MOSFET and P MOSFET, they are isolated, and we have to provide the metal line to connect them. So once again we do the patterning, then after patterning, then metals are introduced. So after metallization, we have certain line, and then who decide this is ground, and who decide this one is VDD? In this structure, it is not determined whether this is ground or VDD. Of course, ground and VDD is provided from the external world. So there is a large battery, so here, and the real ground, and this metal line is once again connected through metal line and another metal line. So that's the reason eventually this part, and this part is biased as a VDD, and this part and this part are biased with the ground. So this is a long story, but anyway, this is a metallization. And although we have shown only the first metal line, usually called as metal 1, but we have plenty of layers in the real technology. We have the number of metal lines in more than 10 layers are existing in current technology. So we have so many chances to wiring this kind of metal lines. So okay, so now let's go to the layout, but that was all for our CMOS fabrication. So as you can see, although we have shown it for a simple circuit CMOS inverter, but even though we have different logics, However, the basic principle is the same, so we have no discrimination between inverter and NAND. Just the difference was coming from the mask. When the mask is different, then the final shape will be different. So designer should suggest which should be the suitable mask pattern for them for the fabrication, and that is done by designers. Okay, and let's go this way. Layout is just to show that how can we fabricate our device using masks. So that is this figure 1.40 shows a typical graph for our CMOS inverter. So as I told you before, we can introduce many different views to consider our CMOS inverter. One is just a logical gate. Wow, this is quite simple. After that, we can think about the connection of two MOSFETs. That is a circuit schematic. And um, Tuesday and today we have seen the cross-sectional view. So cross-sectional view of our P MOSFET and N MOSFET. But in order to make it, then we have to make a certain recipe to the fabrication guys, and that is the map of kind of a map of our recipe or our view for this kind of a CMOS inverter. So if we give it to the fab, then using this map, then they try to fabricate the circuit, and the circuit will be acting as the CMOS inverter. Then please have a look at these graphs. How can you understand this is the inverter? So, here we have a certain part shown in the gray reason in this black and white one, but usually we use some colors to represent this one. But anyway, this is corresponding to your N well, and all other part is p-type substrate. Then what I can say is, although I have a little information about this technology, maybe we can find something related to the P MOSFETs only in here. Maybe this is the place for P MOSFET. And if we have something here, this is not related to the P MOSFET, because P MOSFET is built on the N-type well. Yeah, now you know it. And here you can see that here we have a long line, and this line is connected to the A signal, and A signal is in this textbook usually used to represent the input signal. And now this A signal is propagated here downward and upward, and here we can see certain structure. So let me just draw once again. Here we have certain structure, and we understand A signal is coming from the tap here, and we have something like this here. Now I'm drawing the magnified view of this guy, and now you can see that this is corresponding, and this is corresponding to the source of your P MOSFET and drain of your P MOSFET. Why this is source and this is drain? Because this part is connected to the VDD. So source of your P MOSFET is connected to VDD, and the remaining part is connected to your output. So this one is working as your drain. So similarly, you can find also MOSFET here. Where can you find the MOSFET? Can you point it out? So you can find that this is your MOSFET. Still, you have a signal, the gate, and the gate is driven by your A signal, and one diffusion is connected to the ground, and another one is connected to Y. So that is once again another transistor called NMOSFET. So now from this layout, you can understand if we draw it in a schematic way, then that will be the drawing. So here we have two numbers for both the MOSFET and PMOSFET. Usually this first number is representing the width of your transistor, and second number is corresponding to length of your transistor. So please, what is the length? You understand what is the length and width of your transistor. Length is corresponding to the distance between your source and drain. So typically in many cases we want to keep it as short as possible. So for example, if we have 65 nanometer technology, then that will be about 50 nanometer. Of course, nowadays every day you from the news headline, you say that you hear like 3 nanotechnology, 2 nanotechnology, and sometimes 7 nanotechnology. Although the physical length itself is not exactly 5 or 3, 7, but still its length is about just 10x nanometer. But you know, 10x nanometer is still already quite a short distance, so please note that this distance is the shortest one you can find in your technology. And yes, this is corresponding to the length. And then where can you find the width? The width is, this is the width is width of your transistor. So CMOSFET or MOS technology has very good properties. Like, please look at it. Originally I had made a transistor like this. Yes, now it works, but I wanted to double the current. I wanted to have the twice powerful device. Then what we can do is simply increase the width of your transistor twice wide one. Then what will happen? You can expect that the current of your transistor is just doubled with your increase in the width. So simply speaking, if you scale up and scale down of your transistor width, then you can easily change your current for drain. So this is quite good because as a designer you have many freedom to select your device size. For other technologies it is not that obvious, so there is some limitation. So anyway, please note that you have two different numbers, width and length, and this is length scale and this is width scale. Then let's come back to our PMOSFET and MOSFET. Then you can immediately find something a little bit tricky here. Which one is bigger? Do they have the same size? Or you can find that this one, row 1, MOSFET is in this sense thinner with smaller width, and this one has wider width. Oh, why? It is because is because the property of our silicon material. Silicon material has also holes and electrons inside it. However, in the case of silicon material, usually electrons has higher carrier mobility. What is the mobility? I will explain later. But anyway, compared with these holes, electrons moves quickly. So therefore, if we make really balanced transistor for and PMOSFET and MOSFET, then unfortunately this MOSFET is twice or 3 times more stronger than this PMOSFET. So as you know, our CMOS complementary CMOS logic is done by pull up and pull down circuitries, and the operation was done by the winning of only one circuitry. When pull up is winning, then output becomes VDD, and when pull down is winning, then output becomes ground. So therefore, since these two circuitries are working together and competing together, the best situation is they are well balanced. Both of them are in the same size, same size means that same performance, and then we have a quite much balanced one. But if we make the small sized one, let's say that our PMOSFET is now become just unit size instead of this twice wide one than MOSFET, then what will happen? Now we have strong pull down and relatively weak pull up. Then what will happen? Now when the signal, output signal is close to 0, it's okay. The signal is going down to logical 0 quite quickly. Good. However, if we have a relatively weak pull up, then now this rising edge will take longer time, because the strength of our pull up circuitry really determines how fast we can charge our output node Y node to the VDD level. And if you don't have the balanced one, then you will have severe unbalanced behavior between this pulling down and pulling up behavior. You may say that, okay, even though we have a slow reaction, but still here we have a fast reaction, so it's good. No, it's not. The best way is just a balanced one. I would rather having just a balanced one instead of having this highly unbalanced one. So please note that. That's the reason why usually we introduce different width for our PMOSFET and NMOSFET to balance the strength of our pull up and pull down circuitry. Are you with me? And it really depends on the technology. Previously, the silicon's electromobility and hole mobility shows somewhat difference, so even twice or even 3 times difference were observed. However, as technology evolves, so we have invented a way to boost up the hole mobility in the PMOSFET, so the difference gap is not as high as just all the times, but still we have differences. Okay. Then now here, what is the number 2 and number 8 in this case? 2 and 4. This is 2 micrometer, or 2 nanometer? No, maybe not. Then what is this number? This number shows certain integer multiples of a certain unit length, lambda. And here lambda is typically given as half of minimum feature size. For example, if you have 180 nanometer technology, then your lambda is 90 nanometer. And then the shortest length you can achieve is what? The shortest length you can achieve is for as a gate length is 2 times lambda. So here 2 times lambda means that actually you have used the shortest gate length for your M MOSFET and your P MOSFET at the same time. Then only the width are differed in order to compensate the difference of your electron mobility and hole mobility. So usually in many cases in the digital circuit, we try to have the shortest gate length. The shortest gate length is good for, first of all, good for our area. If you have a small device, then you can save your silicon area. Also, it is known that if you have a short distance, then your device speed is higher. Wow. And another one is, or you can, since you have a shorter one, then you can have also narrow device. I mean that. So later we will see that the current of your transistor is heavily determined by this ratio, width and length. So if this number is 4, then more or less the current is the same for same technology. But point is, let's say that you have 2 lambda over 8 lambda. It is number 4. However, you can achieve same number 4, same ratio 4 by introducing, for example, 4 lambda and 16 lambda. Wow, you can have this one. Then what will happen? In order to achieve the same power or same current drivability, then your area should be not twice longer, but compared with this one, your length should be doubled and width is also doubled. So you have 4 times penalty in your area. Okay. Then if you have 4 times wider device, then unfortunately you have also increased capacitance. So in order to charge and discharge this larger capacitance, you need more time. So also power consumption point of view, it's not good. So usually we wanted to have the shortest length. So if every device has the minimum length, then only the difference is simply given by this width. So here the simplified notation shown here just shows the width ratio. So 2 means that usually this is the minimum size for over 2 is regarded as the unit size. Then it means that 1 is this one is a unit size, and this 2 means that only the width is doubled. So this is the simple notation shown here. But anyway, important thing is we wanted to consider or use in many cases in digital circuit the shortest length transistor. So now there is a cell design called standard cells. This is not done by you. I mean that done by you designers. This is sent from fab guys. So for example, if you make a contract with a certain fab, then after the contract is made, then they send you PDK. Then PDK contains some standard cell designs. It means that if you wanted to draw or if you wanted to use your inverter, you don't have to draw your inverter, because for such kind of a frequently used designs, so fab guys already provide predefined layout. Then you can just use it, or even automatic design is possible. So in this case, standard cell design methodology, usually we have something like this. Here we have a upper part and lower part, and upper part the VDD line runs horizontally, and here we have ground line running horizontally, and between them, since our technology always consider PU, pull up and pull down, and pull down is usually done with N MOSFET and pull up is done with P MOSFET. So here N is related with N diffusion layer, and this is related to P diffusion layer. So you can see that between them, here you have a certain running lines for your P MOSFET. So P diffusion, and there is another line, another level for N diffusion. So when you have the N diffusion here, then just crossing your gate signal, and crossing your gate signal, what will happen? Then each of them become a P MOSFET. And when you have an N diffusion, and when your gate signal cross over vertically in this N diffusion region, then you have N MOSFET. So in this standard cell design approach, then you can find that, okay, here is a VDD line, power rails, so-called, and ground line, power rails, and here you have a level for your N diffusion, and level for your P diffusion, and here you have an N diffusion, and usually gate is running only vertically. So therefore, what you can do is, please try to identify your transistors in this layout. Then what you can see is, okay, this one is corresponding to one P MOSFET, and this one is corresponding to your PN MOSFET, and this one is minimum sized, and also here we have a minimum sized one. Okay. So this is another example of a NAND tree. NAND tree means that although that is NAND, but here we have 3 inputs. So first take A, B, C, take their AND, and take the inverse as a Y. This is NAND 3. So then, first of all, before considering our layout, please consider what should be the schematic. So in this case, we have inverse operation, okay? Then from this ABC operation, now we can consider our pull down circuitry should be given as 3 serially connected N MOSFETs, A, B, C. Then only when A, B, C, 3 of them are 1, then we have a connected line toward ground, so the output value Y becomes 0. all otherwise case, following the conduction complement rule, all other cases we will have the connection to the VDD, so output will be just logical number 1. So this is the circuit schematic we can expect. So if we just convert it to our layout, then now we expect that our transistors are serially connected. Then please try to find it. So in this layout, then where can you find your Y? Oh, here you have Y, and this is all Y, and you can see that still this part is Y. And where can you find your ground? Okay, this is ground, and this is so ground. Now we are talking about this point and that point. In between, what happens? Now you have the running line of N diffusion, and you can find that this one is one transistor, this one is another transistor, and this one is also another transistor. And this first transistor is driven as gate signal A, and its source is connected to the ground, and you know this part now becomes the drain of your A transistor. Oh, now you understand. This is driven by A, and this point, let's try to make a symbol like a star, and here we can find a star. And for the second transistor, now this star symbol part is working as source, and this is driven by your B. Oh, now you have B, and here you have here V side 1, and now this is corresponding to your B side 1, and this part is once again used as the source of your third, the last one. And this is driven by C, then eventually it is connected to your Y. So you can easily understand the lower part related to N diffusion region is corresponding to a serially connected 3 transistors. So that is one. And how about then pull-up device? Then pull-up circuitry, you have to have, in order to make the conduction complement, now you have to have one transistor directly connected to the VDD. So VDD, and so this is of course PMOSFET, and another transistor also connected, directly connected to VDD, and finally another one, the last one, directly connected to the VDD. So of course 3 of them are driven by ABC. Then how can you achieve this goal? So please have a look at this upper part. So are you all with me? So if you have any questions, so I always encourage you to give me any question. Now here we have Y. So if we have a look at this point, then here we have Y, and ground, VDD runs not only to this part, but also here this part. So when you have a look at this C-driven PMOSFET, it has VDD and also Y as its source and drain. So simply speaking, this one is driven by your C1, and output is Y. Already that is done, but more interesting is happening in this B part. B part, where is the source of this B transistor? This B transistor here is the source of your B transistor, because which one is source and which one is drain is not determined from its structure. It is determined by the relative value of your applied bias. You know, VDD is the highest value we can expect in this circuit. So therefore it is certain that this part is working as the source for your transistor, any PMOS transistor. Okay, so then this one is now should be the drain of your B transistor, and this B transistor's drain is also connected to the Y. So if we have B transistor here, still we have source connected to the VDD and drain connected to Y. Okay, we have done for the middle transistor, and let's go to the leftmost one driven by A. Here we have P MOSFET driven by A, and also it's one part is connected to the VDD and that is connected to the Y. So although it is not that obvious as in this NMOS case, however, when you have a look at and when you just investigate it, then you can find that these P MOSFETs are parallelly connected to each other. Okay, so that is the way we introduce 3-input NAND. Of course, it is not invention by one genius, but there are too many persons who are involved with this kind of things. Okay, so nowadays, as a engineer working in 2020, so we can use this one without much difficulties. So now we have only 8 minutes left, but I wanted to start the chapter 2, and chapter 2 is now devoted to MOS theory. So I expect that most of you already attended the course, the microelectronics course. Have you? So you have already attended the microelectronics course or semiconductor materials and devices course. So I expect your previous knowledge on the CMOS technology, but anyhow, I will try to explain from the beginning. So if you have no previous exposure to this kind of discussion, then please do your best to catch up the contents, because this was already done in your junior level courses. So anyway, although I have covered this slides in our very first lecture, lecture 1, I have to repeat this one once again, because this is related with fundamental understanding on your MOS transistor. So MOS transistor is actually using the MOS structure, MOS structure, and later we introduce source and drain here, source and drain. So before talking about the role of source and drain, we have to concentrate on this MOS structure. As I told you before, the purpose of this MOS structure is just changing your gate voltage. You wanted to control the number of mobile carriers in the beneath of this oxide layer. That was it. So if you introduce higher voltage, then what you wanted to do is just to increase the number of electrons here. And what you wanted to do is, when you decrease the gate voltage, you wanted to reduce or decrease the number of electrons in the beneath of here. So the ideal case in digital scene, not analog, in this case your gate voltage can be either VDD or ground. And what you wanted to have in ideal case is, you wanted to have almost no electron error when you apply 0 to your ground, and when you apply VDD, quite high voltage, then you wanted to have the maximum number of electrons you get. Okay, so this is your desire to have this MOS technology. Then, you know, which one is difficult? So I want to ask you, you have two different purposes. One is when you apply high voltage, you want to have many electrons. That is one. Second one is when you apply zero voltage, you want to have zero electrons. Which task is difficult, more difficult to get? I'm certainly saying that this is important. When you apply 0 volt, having no electron, that is critical one. That is the importance of this MOS structure. So think about this one. You also make such kind of capacitive structure using MOM structure. So when you apply higher voltage, then you can get more carriers, more positive carriers, and more negative carriers. And these negative carriers are of course provided from your electrons. So it is not that difficult to gather more electrons when you apply high gate bias. But point is, can you shut down this capacitive structure? Let's say that you apply 0 volt. Wow, what will happen? So there is no potential difference between this upper metal and lower metal. Then do you have no electrons in this lower part? That will be used as your conducting layer. It's not possible. In this MOM structure, you always have mobile carriers, and it is impossible to shut down your transistor or your possible conducting device. However, in the case of MOS system, now you can achieve the state where although you have a certain amount of charge, but no electrons are found in this case. That is, I think, that the beauty of this MOS system. So with this capability to shut the system down, that is the way. Then how can we achieve this goal? So as I told you before, maybe you remember the graphs I have shown in the very first lecture. This MOS system is good because its silicon part, semiconductor part, can have two different mechanisms to provide charges. One is, in this case, one is electrons. That is quite easy to understand. If we have more electrons, then we have more negative charges. However, there is also another mechanism. So, holes. I mean that less holes are corresponding to also negative charge. Why? Because semiconductor material, this part is built on our p-type substrate. So p-type substrate means that there are many means that typically 10 to the 17 or typically 10 to the 18 per cubic centimeter negatively charged borons are existing in your boron atoms. Boron atoms are existing in your system, and initially it was counterbalanced by the same amount of holes. Of course, holes are positively charged and boron ions are negatively charged, and their numbers are the same, so they were perfectly balanced. However, if we have less holes, say that we have no holes anymore, then what will happen? In this case, net sum, we will have actually negative charges for this semiconductor system. So are you all with me? So that's the reason why, even though we wanted to get negative charges in this semiconductor, why we wanted to have a negative charge? Because gate is positively charged. This is positively charged, and we wanted to collect positive charge in this gate, and we wanted to get negative charge in this semiconductor part. And semiconductor part anyhow should provide negative charges, but fortunately this semiconductor can have two different mechanisms to provide negative charges. One is, oh, first of all, previously I had holes, but I will just remove my holes. Then I can provide required negative charges. Only after some bias voltage, then now the second mechanism is activated, and this directly provides your electrons. Okay, so as you can see here in these graphs, you can find the voltage, x-axis is voltage, and charge density. And this green line is corresponding to the electron density. Electron density, even though your gate voltage is increased from 0 volt, but this mechanism providing electron, the second mechanism in my terminology, does not activate it. Then who provided negative charges? You know, here we provide negative charges from this blue line. And what is it? This blue line is just less holes inside the semiconductor region. So at the beginning, close by the 0 voltage, then first of all this semiconductor substrate try to match the required negative charges by the depletion mechanism, so less holes. However, beyond a certain point, now this point or this first mechanism becomes too ineffective, and next more effective mechanism comes in. This is the providing electrons and called as inversion mechanisms. So that's the reason why we have positive threshold voltage here. So fortunately when we apply 0 voltage, then we have no electron at all. In my opinion, that is the beauty of our CMOS technology. So we can have a positive threshold voltage for it. Okay, so sorry about 4-minute delay in my wrap up, and if you have any question, then please give me your question just after the end of this session. Okay, thank you, and see you next Tuesday. So in the next Tuesday we will start our routine homework procedure. So the very first homework will be distributed in the next lecture. Okay, thank you, bye.
이렇게 전자는 이제 피 서브